To the first question. Do you think that there'll be an equal number of salmon at each weight? Do you think that there will be two modes? So a lot of salmon will be here and here, but not so many at the ends. Or do you think that most of the salmon will have this middle? You think it's A, B, or C?
C.
Yeah. So heights of almost any living thing are normally distributed, with most heights being in the middle, and then of course some that are very big or very small, but most are in the middle. So the mean was 4.73, which is like a little bit more than 4.5. So I could just like approximate it's about here, right? And the standard deviation was 0.53. Okay. And we can use those to make some approximations based on what we know here. But this is a normal curve. Like you would need to actually use some higher math to get exact answers. The first answer I can be pretty sure of though, because I can see the 6 right here. And so how can we use it to estimate the proportion of salmon that weigh more than 6 kilograms? It looks like it's about how many?
0.
About 0, right? Close to 0. Okay? Close to 0. Between 4 and 6 kilograms. Anybody want to shoot an estimate at us? Between 4 and 6. So we would be talking about this here. I think 75 is a pretty good estimate. Anybody have another number that's close to 75? I was thinking 75 to 80. Yeah? Okay. So 75, 80, anything in there is going to be pretty good. So about 75 to 80%. We're just observing. We're not actually calculating at this point. How can we find the weight which 90% of the salmon weigh less than? So 90% weigh less than means we're going to be pretty far to the right. Okay, anybody have an estimate for us? 5.40. Anybody else like 5.40? Okay, I think I like that number a lot. It was actually right in between my estimate and Ms. Young's estimate, so I'm going to go with that one. 5.4 kilograms, approximately. Again, remember, we're just approximating. 25% of the salmon weigh more than. So again, we're on this side with 25% weighing more than. Anybody have an estimate for that one?
4. Because we said 75 or between 4 and 60.
75% are between 4 and 6.
75 would be less than 4.
Okay, but it says 25% weigh more than, so we're on this side. Yeah, so I think about 5 is fair. About 5. Okay, these are estimates. If you strongly disagree, you can tell us, because that would be fun. But you should have numbers around those. Like if we say 5, you shouldn't say 3. But if you want to say 5.5 or 4.5 or something like that, like maybe we can argue one of those. Okay? But we're going to be able to calculate a lot more closely today. So it seems like a lot of you are ready to turn the page, which is excellent. Let's turn the page. And we're going to talk about normal distribution. It says introduction to normal distribution, but hopefully you did have an introduction in Algebra 2, so it's not the first time you've seen it, but it might be, and that's okay. So not everything in the world is normally distributed, but a lot of things that happen naturally are, like heights of things that grow. So we consider variables with symmetric, bell-shaped distribution, and we call these a normal distribution. It's the most important distribution in statistics. Normal distribution. All right, Normal distribution arises in nature when many different factors affect the value of a variable. Here are some examples of quantities that might be normally distributed. Heights of 16-year-old boys, especially if you take a large enough group. If you just take a group of like 5, maybe not. Maybe they'll all be very tall or all be very short. But if you take a large group of 16-year-old boys, then their heights will be normally distributed. Lengths of adult sharks, yields of corn or wheat. So a farmer might have 1 year a whole lot and another year very little, but if you take all the years together, you might find that they're normally distributed. The volumes of liquid in soft drink cans. So it says 12 ounces in your soda, but it's not ever going to be exactly 12 ounces. It's going to, according to the measuring device, it might sometimes look like it's 12 ounces, but it really might be like 12.00001, right? So these volumes of liquid are normally distributed. The weights of peaches in a harvest and the life of batteries. Okay, all of these things normally distributed. Good?
Yeah.
Okay. All right, the normal distribution curve. Although normal distributions have the same general bell-shaped curve, the exact location and shape of the curve is determined by the mean and the standard deviation. So the mean, which is mu, which measures the center of the distribution, and the standard deviation, which is sigma, and it measures the spread of the distribution. So the mean tells you where the middle of your curve is. The standard deviation tells you how spread out that curve is. All right, here is some notation. So if you see this notation, you'll know that we're talking about a normal distribution because of the n. Last class we talked about a binomial distribution. It had a capital B. This one has an n. So we say that the mean and the standard deviation are the parameters of the distribution. And the probability density function, which is the curve, is called the normal distribution curve. Normal distribution curve, or just normal curve for short. And that little squiggle or tilde is read as is distributed as. All right, so here are some fun facts about the normal curve. The normal curve is symmetric along the vertical line, x equals mean, right? Here's your mean. So the two sides are symmetric. F of x, which of course means y, is greater than 0 for all x. So you're never going to have it go below the x-axis. The x-axis is, in fact, a horizontal asymptote. Okay? We're going to turn the page. And on the next page, we have the percentages more precise than I have ever seen. So these are more precise percentages than we use for our estimates. The ones that are on my board are approximations. They're commonly accepted approximations. You'll notice that they're not even rounded values of these. Like 13.5 is not a rounded value of 13.59. But they're commonly accepted approximations to use because people don't walk around carrying these numbers in their head. But they do actually. Some people walk around with those numbers in their head. There's not that many of them. There's 34, 13.5, 2.35, and 0.15. And then the other side is symmetric, so you only have to remember one side. Okay? But if you were given this curve on an exit ticket or on a test, if you're given this curve and asked to use it, then you should use these numbers. Otherwise, you can use the approximated numbers. Okay? Okay. So the approximate numbers are 0.68, which is 68%. Okay. 95%, 0.95, or 95% are within 2 standard deviations of the mean. So from 2 below to 2 above, that's 95%. And then 99.7%, which is 0.997, 99.7%, are within 3 standard deviations of the mean. So, oh yes. So when you're talking about, say for example, people's heights, right? If we have people whose heights are the mean, there are going to be a lot of people around that. And there will be still a lot of people that are within 1 standard deviation, 2 standard deviations of the mean. But then once you get past that, there are very few people that are more than 2 standard deviations from the mean, and a very, very small number of people who are more than 3 standard deviations from the mean, whether they're above or below. All right, so we're going to do some example problems, and when we do these example problems, we're going to draw a normal curve for each one and shade, and that's often what's done in these problems to help you wrap your mind around the percentages that you're getting, so you can understand where they're coming from. So the first one says a sample can of peaches was taken from a warehouse. The contents of each can was weighed. The sample mean was 486 grams and a standard deviation of 6 grams. And so to answer these questions, sometimes they have you draw it twice. It's just a lot of drawing for me. I'm going to draw it once in the middle. So you're going to do your best to draw a symmetric normal curve. I'm actually quite terrible at this. Okay, and then in the middle is your mean, 486. And you're going to draw 3 standard deviations on each side. 1, 2, 3. 1, 2, 3. And then in order to get the other numbers, you add your standard deviation. So I'm going to add 6 each time. And so 46, I get 492. 498. And 504. And then you'll subtract on the other side. So subtract 6. 480. 474 and 468. And then what we do is we use this to represent our answers. So sometimes it's hard because the questions that they ask might overlap, so you might actually have to draw it more than one time, but this one doesn't. Because for A it says, state the proportion of cans that weigh between 480 and 486. So for A, they're just asking about this part right here. So using the exact values, since I'm provided the exact values, I can say that it's this one, 34.13%. If I were not provided the exact values, what estimate would I give? 34%, good. All right. More than 492, so that is this one, and this one. People always forget that there's one over there. This one, and this one. Okay, so I'm going to add up 13.59, 2.15, and 0.13. Okay, so I just added up the percentages. Notice that I got them from this. So every normal curve will have these same percentages, which you'll use if you're provided them, and you'll use the approximations if you are not. All right, so I started by putting the mean in the middle, and then I added the standard deviation each time on the right and subtracted it on the left. You will always have 3 standard deviations on the right and 3 on the left. Did you guys get the same numbers I got? It's very easy to make a mistake adding and subtracting. Okay, so then how many would you expect to be between 87 and 111? So this one, and this one. And we find your percentages from the top, this plus this plus this. And I got 81.85%. Did anybody get that percent? Anybody else? Okay. There's another step though, because it asks you how many players, right? So if you haven't done that other step, do that now. I'm gonna write down my work. All right. So a couple people are still stuck on their percent button, using a percent button to find a percent. There's not always going to be a percent button in life. So how do you do that if you don't have a percent button? Okay. So I heard two answers that were both right. Move the decimal over, sure. Or divide by 100, which will move your decimal over for you. Percent means per 100. And this is the reason why we do move the decimal over, because that's what happens when you divide by 100 per 100. So if I divide this by 100, I get 0.8185, and then I'll multiply it times the 200 players. And I get 163.7 players, which is impossible, so I'm going to round that to what? 164 players. Questions? Okay. It says find the value of k such that approximately 16% of chess measurements are below k. And because it's using that word approximately, we're probably going to be using those approximate measurements. I mean, you could, since it's approximately, you could use the exact measurements and just choose the standard deviation line that you land on closest to. But these are those measurements, so it would be good to have these in your notes anyway, since they're not always going to be on my whiteboard. All right, so let's use the approximate ones, and let's actually just put those measurements into your curve. I do believe Delta Math uses the approximate ones. We will find that out soon. All right, so we had 34%, of course, 13.5%, 2.35%. And then this little tail over here is 0.15%, which is not 15%. Remember, this is 0.15%, which is less than 1%. And then it's symmetric, so the other side will be the same. 34%, 13.5%, 2.35%, and 0.15%. All right, so 16% of the chess measurements are below the K. So if we add these up, that's going to give me 2.5, and then that's going to give me 16.5. So we're talking about these three sections here, 1, 2, and 3. And I think we already did the work such that we put 95 in the middle. And we put 87 here. So I believe that K would be 87. Yep. $87. There must be a unit on that. Centimeters, yeah. Sometimes I'm going to ask you questions that don't land right on the standard deviations, and so we need other ways to find these answers, okay? All right, so here's a new question. The mean is 40, and the standard deviation is 10, so you can draw a normal curve. Notice it says illustrate your answers. You can expect to be tested and be asked to illustrate your answers as part of your points, so you should definitely be practicing that. So 40 is your mean, your standard deviation is 10, so it's going to be 50, 60, 70, 30, 20, and 10. But what it asks you is the probability that x is between 37 and 48. And those are not standard deviations. So I don't know just by looking at it what those percentages are. 37 is going to be about here, maybe. And 48 is going to be about here. All right, so I know this about here, but I don't know what those percents are because I didn't land right on the standard deviations. So we're going to use the normal CDF function on your calculator, and I'll give you a minute to catch up on writing all of this, and then I want you to find the normal CDF function with second vars. Here's my calculator. So second vars, that says distribution above it. I want normal CDF, so I'll press enter. And it says that the lower bound is -1 E99. It's not really that number. That's their approximation for what? Infinity, positive or negative in this case? Negative, yeah. So negative infinity, remember that the E means times 10 raised to the power. So this is -1 times 10 to the 99, so it'd be really, really, really small. And then the upper bound. But we actually don't want that lower bound. We want our lower bound to be 37 because we want between 37 and 48. So I'm going to type in 37 there instead. And then go down to the next one. And we want between 37 and 48. All right. It says my mean is 0, but that's not my mean. My mean is 40. And my standard deviation is 10. Okay, so all those numbers that I entered, I'm going to write them on my paper before I find my answer. It's going to look like this on my paper. Normal CDF. All right, first you want your lower bound 37, your upper bound 48, your mean 40, and your standard deviation 10. And I'm going to label them in my notes since this is the first time I've done it. Lower bound, upper bound, mean, and standard deviation. Okay? And then once you have that in the calculator, you can press enter and it should give you a decimal answer, which you could also make a percent answer. Okay, so enter. All right, so I got 0.406 with my 3 sig figs, and that's the answer I'm going to put on my paper. 0.406, which is, of course, 40.6%. Okay. The next one says x is greater than 45. And so we're going to do another normal CDF. My lower bound is what number? If it's greater than 45, what's my lower boundary? 45. We want to go 45 to infinity, but of course there's no infinity button. So I could do 1E99. And then my mean and my standard deviation, which stays the same, 40 and 10. All right, so x is greater than 45. Here's my 45 in the middle here. And it's going to be all this, okay? All right, so let's go back to the calculator. Second vars, normal CDF. Yeah, that was my question too.
I don't think you can type these.
You can't?
No, that doesn't work.
Second comma. Second, and I'm looking for the comma actually. Oh, there it is. Yeah, thank you, Osman. All right, so let's go down. Let's try that. 1, second comma, 99. And then the same mean and standard deviation. Yeah, it worked. Taught me something today, thank you. All right, so I'm getting 0.309. Anybody else getting 0.309? Excellent. So what I want you guys to do is do part C right now. Write out what your normal CDF is. Let me switch back. And I also want you to draw the picture, okay? Can't type negative infinity, so we type negative 1E99. And then 26 is your upper boundary, 40 is your mean, and 10 is your standard deviation. Looking at the picture, you're not expecting a very big number. And in fact, I get 0.0808. Anybody else get 0.0808? Okay. Yeah, and then Sophia reminds us that's the same as 8.08%. So at this point, I'm not going to be picky about which format for your answer. I'll have to give you some more specific instructions before you take a test. Yeah.
Oh wait, no. I did 0.81 or 0.081 on accident. Wrong number of figures, so.
Okay. All right. The time it takes students to complete a puzzle are normally distributed with a mean of 28.3 minutes and a standard deviation of 3.6 minutes. Calculate the probability a randomly selected student took at least 30 minutes to complete the puzzle. So we're trying to find the probability that x is greater than or equal to 30. And then after we find that probability, we're going to use it to also do a binomial distribution. So we're going to put these two ideas together, okay? All right, first thing we're going to do, though, is a normal CDF. What's our lower bound? 30, yep. And our upper bound? Infinity. And then our mean and standard deviation. Oops, I don't even know why I was trying to close that there. 3.6. Okay, put that in your calculator. Remember, to get normal CDF, you press second vars. To get the E, you press second comma. All right. Did you guys get 0.318? Okay. So 0.318 is the probability that a student took more than 30 minutes, or at least 30 minutes, sorry, to complete the puzzle. Now we can use that probability in a binomial distribution. So remember last class we learned binomial distributions. And this question is asking that. Out of 10 randomly selected students, 5 or fewer of them took at least 30 minutes to complete the puzzle. So we're trying to find the probability that this happens, okay? So we're going to do a binomial CDF. Okay, and we're going to find the probability that if we have 10 trials, which is the 10 randomly selected students, each one has a probability of 0.318, and we can actually just use our answer button, which would give us this number with all its decimal places, okay? And then 5, because we want 5 or fewer. So remember, the CDF, binomial CDF, would be for 5 or fewer. It would be binomial PDF if we wanted exactly 5, okay? And we're going to calculate now the probability that 5 or fewer took took at least 30 minutes to complete the puzzle. All right.
Answer button?
Second and then negative.
Second and negative, you said?
Yep.
Yeah, okay. All right, so second vars, and then I need binomial, so I'm scrolling. Binomial CDF. 10 trials. Probability. Oh, I don't think I actually put it in. So let's see how different I get if I just put 0.318. X value is 5. All right, so I think my 3 SIGFIDS answer is actually still good, right? Did you guys get 0.938 even using the answer button?
Yep.
Yeah.
Okay.
Doesn't matter when you round because
Yeah. Okay. All right, so that was combining our ideas from before. We're going to move on to z-scores.
Z.
All right, z-scores. All right.
Without any context, you just sound the same.
The reason we use z-scores. Guys, last day of notes, we should be hyper-focused.
I'm hyper, but not focused.
The reason we use z-scores is to standardize things that are on different scales. For example, a really good practical use of z-scores for you might be if you took both the SAT and the ACT and you wanted to know which one you did better on. They publish usually a mean and a standard deviation for scores, and so you could calculate your z-score for the SAT and your z-score for the ACT and then determine which one you did better on. Which one did you do better than more people, right? Maybe on the SAT you did better than 70% of students, but on the ACT you did better than 80% of students. Those z-scores would help you, and they help you by standardizing these values. This is why we call it the standard normal distribution. Okay? All right, so a random variable x is normally distributed with a mean, a mu, and a standard deviation sigma. And for each value of x, we can calculate a z-score. Z-score. Using the algebraic transformation, z equals x minus mean over standard deviation. You should have seen that in a previous class, but if you didn't, it's a pretty simple formula. Z equals x minus mean over standard deviation. All right, and then this transformation is known as the z transformation. That makes it sound pretty cool. Z transformation. Okay. All right, and this is just telling you that if you are considering the mean and then the variance, of course, is the standard deviation squared here, your mean for a standardized normal distribution is 0, and the z-score of 1 is your standard deviation. And you remember when we first opened up the normal distribution on the calculator, it had those values in there. It had mean as 0 and standard deviation as 1, right? Because they're the standard values. All right, the distribution is called the standard normal distribution. Or the z distribution. And the z-score is simply the number of standard deviations x is from the mean. So if you had it all plotted out and each of your standard deviations lines was labeled, then you would know z-score of 1 is your first one after the mean, z-score of 2 is your second one after the mean. Z-scores actually are standard deviations. All right, so we have a similar problem to the one I was talking to you guys about with the SAT and the ACT. We have Kelly who had these 2 scores, and she's trying to figure out in which class did she perform better compared to the rest of her class. So she scored 73% in history, where the class mean was 63% and the standard deviation was 10.2%. And then in math, she scored 66%, where the mean was 62% and the standard deviation was 6.8%. And we're going to find her z-scores to figure out in which one she did better compared to the class. So I'll do history with you, and then you guys will do math and decide which one's better. So for history, the z-score is, oh, thank you. The z-score is x minus mean over standard deviation. So x is her score. So she got 73. The class mean in history was 68. And the standard deviation was 10.2. All right, so let's calculate her z-score in history. All right, are you getting 0.490?
Yep.
Okay. All right, that doesn't seem like an impressive number, but the fact that it's positive tells you that she's above the mean, okay? She's not a full standard deviation above the mean. She's about half above the mean, but she's above the mean, so she did. All right, calculate her z-score for math, and then compare the two to see which one she did better.
So I'm somewhere 99%. Well, was there anything you said right now?
All right, I'm having trouble reading my answer. 588.588.
Yep.
Okay.
If I'm ready.
All right, so she did better in math, right? Because it's higher. Now remember, that's not her score. She didn't score 58%. That just tells you that she's 0.588 standard deviations above the mean, which is not bad. So to make a conclusion, we 0.588 and 0.490. Her math grade was better compared to all right, so we can draw normal distributions with z well. You still have 3 standard deviations above the mean and below the mean, but with z-scores, your curve is standardized so that in the middle, you'll always have 0, and your standard deviations are simply labeled 1, 2, 3, -1, -2, -3. That's what we're going to do here in 6, and then we're going to calculate a normal CDF using 0 as your mean and 1 as your standard deviation, because these are z-scores, okay? So I'm going to start by drawing a picture down here. I do realize that I draw the ugliest normal curves, but I can't wait to see your normal curves. Beautiful. Yep. Okay, remember 0 is in the mean, and then 1, 2, 3. All right, and so I'm going to illustrate between -0.41, approximately, of course, and +0.67, something like that. And then I'm going to do a normal CDF. Yes.
The part C, does it say equal to, but the lower one is not the equal for them?
about probability distributions is that the probability that's equal to any given number is actually 0, because it's like the little line that you're matching there is infinitely thin. So it doesn't really matter if it says greater than or equal to or greater than.
Okay.
Yeah.
Or drawing words. My natural scripture is filled with
All right, guys, we do work at different rates, so let's just be patient with everybody, but I am going to show you these answers, and I'm going to leave them up for a minute, okay? So people who are still working are good. Does anybody have any questions on these answers? So notice for this one we use -1 E99 for negative infinity, and then this one we use +1 E99 for positive infinity. All right, probability that x is less than or equal to k. K is known as the quantile, which I could have guessed, right, because of the title. And if we have the probability x is less than or equal to k equals 0.95, k is the 95th percent quantile. When finding quantiles, we're given the probability and asked to calculate the corresponding measurements. This is the inverse. What does an inverse function do? Kind of, yeah. It undoes the function, right? So it's a kind of opposite, right? So it does the inverse of finding probabilities, and so in this case we use the inverse normal function on our calculator. Okay, so a population of crabs has a shell length x millimeters, and it's normally distributed with a mean of 70 and a standard deviation of 10. Find k, for which the probability x is less than or equal to, or sorry, just less than k, is equal to 0.95. Okay, so we're going to do the inverse norm function, which is also in your second vars. Inv-norm, yes. And it first should ask you for the probability.
It says area.
Yes, so the probability is equal to the area under the curve. And then it's going to ask you for the mean. And then the standard deviation. All right, and then we're going to find out 95% is less than what measurement, okay? I'm going to draw a little picture too. So I know 95% is going to be like over here somewhere. So that's my 95%. And this number right here is k, which we're about to find. So I'm going to put these numbers into the calculator. Second vars inverse norm is 3. All right, so remember, area under the curve is the probability, and that was 0.95. The mean is 70, and the standard deviation is 10. All right, the tail, this should be probably left on left, because if you look at the picture real quick, we're looking for the left of k, okay? So let's see how we do.
Yeah, we don't have the tail.
Oh, you don't? That's fine, because that's what it should be. It should be left. You would have to do 1 minus if you wanted to find right, you know? All right, enter. Why is it not doing anything there? Oh, I have to go down. Now enter. All right. So 86.4 is the value for K. So the probability X is less than 86.4 is 0.95.